binomials that are higher than a second power, so third power, fourth power, fifth power, and so on. And if you do it with the whole FOIL/distributive property technique we've been doing for several binomials in a row, it gets to be pretty unpleasant to do. So, for example, if I have x plus 3 to the 6th power, I got to do x plus 3 times x plus 3 to get something, and then get that product, get the same product, get the same product. That's three trinomials. I got to multiply two trinomials together. That's going to give me some 5-term polynomial times a trinomial. It ends up being about a half a page. So what I'm going to show you today is called binomial expansion theorem. We're going to use Pascal's triangle. It was invented by a guy named Blaise Pascal back in the 1600s, I think. Yeah, before they had calculators. So the fact is, this guy did it without a calculator. If you need a calculator to calculate some numbers, you sure can. But the idea of the triangle, it's real simple to make the triangle. All right? Being able to make the triangle gets you some specific numbers that are helpful in the expansion, and then the actual answer is constructed in step 2. We're going to make the answer in step 2, and I'm going to have you guys understanding what this means, and we're going to be using a lot of the same stuff we've been using as far as simplifying stuff to get to the final answer. So, first thing, making the triangle. Anytime you need to make the triangle, you can. It just starts off with a 1, 1, 1. If you remember that much, you always have ones on the outside. To get the next number down, each row has one more term. To get the next number down, you simply add the numbers above it. 1 plus 1 is 2. Put a 1, put a 1. 1 plus 2 is 3, 1 plus 2 is 3. Put a 1, put a 1. 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4. Right, so that's just how you can construct it. You can go down as far as you have to go. This is kind of ridiculous down here, but I copied it off the internet. I didn't make this myself. Usually we stick to about the 7th power or less. So usually around here is where it stops as far as we're using it. But again, if it goes beyond that, you got this all the way down to the 13th power. So when I'm looking at Pascal's triangle, there's two ways to determine which row you're going to use, because you're going to use one row of the triangle to do a binomial expansion. All right. First way is if you look at the power in your problem. So the structure of the problem we're going to be working with here is some binomial structure raised to some power. That's what the structure is going to be. Technique 1 to find the correct row to use is whatever n equals, whatever that power is. You pick the row that has one more number than the power. So if the power is 4, you want to pick the row that has 5 numbers in it. So 1, 2, 3, 4, 5. If it has 4, fourth power, you go to the one with 5 numbers. If the power is 6, you want to go to the row with 7 numbers in it. 1, 2, 3, 4, 5, 6, 7. That's what this describes here. All right? Because that's easier to describe than the other way. In words, I can describe it in pictures very easily. This row right here should match your power. Second power, third power, fourth power, fifth power, sixth power, seventh power. Every one of those numbers, if you count the terms, 2, there's 3 terms. 3, there's 4 terms. 4, there's 5 terms. Every number in this second row, the second number in the list, is exactly one less than the number of terms. So that's the two ways. Match the power up to the second number, that's the row you're going to use. To get the answer, here's how you construct the terms. Here's term 1, then it's plus term 2, plus term 3, and so on. All right? PT number means Pascal's triangle number. You just picked a row, whatever row you're going to be on. Put the numbers down as you see them. So if I, for example, picked this row, PT number 1 is 1, PT number 2 is 4, PT number 3 is 6, and so on. A is whatever the first object is. It's being raised to whatever n is, so it matches that. B is whatever the second object is. It's being raised to the 0 power. Then every other term, the A, notice the power was n, now it's 1 less. B, the power is 0, now it's 1 more. So we're making the powers go down for the first object, we're making the powers go up for the second object as we construct each next term. Once you've written out the answer, last step is to simplify every object as much as possible. All right, that's step 3, make the answer pretty. So step 1, pick the right row. Step 2, write the correct answer. Step 3, make it pretty. There's your process. So let's try it out. So if I see a power bigger than 2, because we have a shortcut for the second power, right? We learned that already. We used it yesterday and a couple weeks ago. So if we have a power bigger than 2, I want to use Pascal's triangle. And again, I want you to get comfortable with building it. So 1, 1, 1, 1, 1. What goes here? 2, because 1 plus 1 is 2. 1, 1. What goes here and here? 3 and 3, right? And notice this is a 3, and the second number is a 3, right? That's the row we need to get to. All right? So my Pascal numbers for this specific power are going to be 1, 3, 3, and 1. Those are the numbers I'm using. This is the row I'm using. All right? So now to construct the answer, I take my first Pascal number 1. I take whatever this object is, which is x, and I raise it to this power. And I take whatever this object is, sign matters, it's positive, so positive 3 to the 0 power. That's how you make your first term. You pick the first Pascal number, you got the first object to whatever the power in the problem is, you got your second object to 0. That's where you start. If you get your starting term correct, everything else is pretty easy after that because it's a pattern, it just follows the pattern. So next number is what? Next Pascal number over there is 3. So we write down 3. And again, I need x and 3. Every time it's going to be the same two things in the parentheses, x and 3. The first object is going to count down. We start at 3, we count down, we're going to get to 2. The second object counts up, we start at 0, we go to 1. Make it smaller, make it bigger. As we go that way, first object gets smaller, second object gets bigger. X third, x second, 3, 0, 3 first. Then put a plus sign. Always, always, always put plus signs. If minus signs happen, it happens because one of these numbers is negative, and they'll happen in the evaluation step. All right? Always put pluses when you're building it. Next number in the expansion, we did the 1 and the 3 already, so the next number is 3 again. And we're going to write x, we're going to write 3. X to the third, x to the second, x to the
1.
first. 3 to the 0, 3 to the first, 3 to the second. All right, so again, it's just a pattern here. We're just building each term in that manner. The final number in Pascal is 1, so we write the 1 down. We got an x, we got a 3, and again, we got x to the third, second, first, 0. 3 to the 0, first, second, third. All right, when you get accustomed to that technique, that takes about 10 seconds to build those answers. Maybe 20 seconds if it's a higher power. But again, the numbers come from over there, 1, 3, 3, 1. So just to highlight, 1, 3, 3, and 1, 1, 3, 3, and 1 came from there. The x's to powers, x to the third, x to the second, x to the first, x to the 0 came from here. And the power that we start off with is what matches. And then the 3, the positive 3 came from there, 3, 3, 3, 3. We always start the second object at 0. So this always starts at that, 3, 3, 3, 2, 1, 0. The other one starts at 0, 0, 1, 2, 3. Everybody comfortable with how to build that? That's the second step. That's the one that tends to confuse people with anything.
How'd you pick that row?
The second number in the row matched my power. All right, so once I do that, now it's a matter of simplifying. This is just simplification of objects, the same way we've been doing it here recently. So I've got all this stuff being multiplied together. Powers happen before multiplication, right? What's 3 to the 0 power equal?
0. 1.
1. All right, 3 to the 0 equals 1. 1 times x to the third is x to the third. What does 3 to the first power equal?
3.
And 3 times 3 is?
9.
So plus 9 x to the second power. Each case x is just to a power, so we just have to attach that to our numerical answer. What's 3 squared? 9 times 3 is?
27.
27 times x makes plus 27x. And what's 3 to the third power? 3 times 3 times 3, 27. What's x to the 0?
1.
1. So 27 times 1 is 27, and just like that, that's our expansion. That's the answer. Pick the right row, write the correct answer, make the answer pretty. That's how you do it. This is a technique that will take, when you get good at it, you'll get this problem. This problem will take you less than a minute. This is an ACT problem here. If you know what you're doing with this Pascal's triangle technique, it takes you 23 seconds. Obviously, it took more than that to record it, to explain it and everything, but once you understand how to do it, 23 to 30 seconds is how long it takes to do this problem if you know what you're doing. If not, you got to do it the long way. That takes 2 minutes. Still get the right answer, but you've also cost yourself a minute. So again, keep in mind that's how ACT works. They want the people who know all the techniques to get a better score than those that don't know all the techniques. Demonstrates more knowledge.